Hello, and welcome back to the Quantum Slumber, a quiet little channel where we let the strangest ideas in physics slow down enough to fall asleep beside them. Tonight, I'd like you to think about a simple question. How close can we really look at reality before the idea of distance stops making sense? We're used to thinking of space as something we can always divide. Half the distance, then half again and again, forever. Take a ruler, cut it in half, then cut that piece in half, and so on, without end. On paper, it sounds easy. But our best physics says there is a point where that story breaks. There is a scale so small that our rulers, our equations, even our idea of here and there begin to fail. Physicists call it the Planck length. It's about 1.6 times 10 to the minus 35 meters. If you blew up a single proton to the size of the Earth, the Planck length would still be smaller than one tiny atom on that Earth. Down there, something strange happens. Quantum uncertainty and gravity, two theories that usually live in separate worlds, start to collide. Space-time stops behaving like a smooth fabric and starts to flicker and jitter, as if the coordinates of reality were made of static. Push your view any closer, and the energy you need might be enough to make that tiny region collapse into a microscopic black hole. Tonight's journey is about that edge. What happens to distance when no measuring stick can survive? Why does trying to see more eventually cause the universe to push back? And why do atoms, light, and the fabric of space-time all seem to obey the same quiet rule about how small can be? We'll follow that rule gently. We'll start with microscopes and wavelengths, with the simple connection between energy and resolution. And step by step, without rushing, we'll walk all the way down to the point where our best laws stop cooperating, and the concept of distance itself begins to blur. Before we dive in, you don't need to do anything complicated. Just let your body get comfortable wherever you are. Let your shoulders drop a little. Let your breathing settle into a slow, easy rhythm. You don't have to stay fully awake. Your curiosity can stay just alert enough to follow along while the rest of you drifts. If this kind of slow, late-night physics helps you relax, a gentle tap on, like, or subscribe is a small gesture, but it means a lot. It tells the algorithms that there are people who enjoy calm, thoughtful stories about the universe. And it lets me know that somewhere out there, a mind like yours is listening. If you'd like, you can also share in the comments where you're listening from tonight, your city, your state, or just the time on the clock beside your bed. For now, let's begin at the surface of the microscopic world and follow one simple rule. To see smaller, you always have to use more energy. When people first began to wonder what matter was made of, the instinct was simple. Build something that lets us see smaller. A clearer lens, a sharper focus, a better microscope. It feels almost obvious that if you keep improving your instruments, the universe will keep revealing more and more detail, like zooming into a photo on your phone. But down at the smallest scales, nature plays by a different rule. Every microscope is limited by the waves it uses. With visible light, those waves are a few hundred nanometers long. That's small compared to a human hair, but enormous compared to an atom. An atom is about 1/10 of a nanometer across. Asking visible light to show you an atom is like trying to read the fine print on a contract using finger paint. The brush is simply too big. You can picture it another way. Imagine standing beside a swimming pool. You throw a big, slow wave across the water and ask, "Can this wave tell me the exact shape of a pebble at the bottom?" Of course it can't. The wave washes over everything, smearing out the details. To pick out the pebble's outline, you'd need ripples much smaller than the pebble itself. That's exactly what happens with light. A wave can't reveal features that are much smaller than its own wavelength. To see finer details, you have to use waves with shorter wavelengths. And in the quantum world, shorter wavelength means higher energy. This is the heart of the rule physicists quietly follow. The smaller the distance you want to probe, the higher the energy you have to use. Once that idea took hold, people began to look for new kinds of waves. In the early 20th century, physicists learned that matter itself, behaves like a wave. Electrons, which we tend to picture as tiny particles orbiting a nucleus, also spread out like ripples with a wavelength that depends on their momentum. Increase their energy, and their wavelength shrinks. That insight turned electrons into a new kind of light. In the 1930s, Ernst Ruska and others began using beams of electrons instead of visible light inside microscopes. Because electron wavelengths can be made much shorter than those of visible light, the images suddenly sharpened, structures that had been nothing more than blur under a regular microscope. Cell membranes, tiny organelles, fine details, and crystals came into focus. The world beneath the glass slide became more intricate than anyone had imagined. But even that wasn't the end of the story. If you keep pushing the idea, a microscope doesn't have to look anything like the instruments on a lab bench. A particle accelerator can act as a microscope too. Instead of gently illuminating a sample, you fire a beam of high-energy particles at it and watch how they scatter. The pattern of deflections carries information about what's inside. At places like the Stanford Linear Accelerator, electrons were hurled at protons with energies far beyond anything in a traditional microscope. If protons were simple, solid balls of charge, the scattering would have looked smooth and featureless. Instead, the electrons bounced as if they were hitting 3 smaller, concentrated spots inside each proton. Those experiments were the first clear hint that protons are not fundamental at all, but bundles of even smaller entities, quarks bound together by the strong force. What had seemed like an indivisible bead of matter turned out to be a restless storm of quarks and gluons, constantly exchanging energy and momentum. To get that glimpse, physicists had to go to extremely small distance scales, far smaller than the size of an atom. And they did it not by carving tinier rulers, but by pouring more and more energy into their probing particles. Higher energy meant shorter effective wavelengths, and shorter wavelengths meant finer resolution. By the time you trace all of this history, from glass lenses to electron beams to long tunnels filled with accelerating cavities, the pattern is hard to miss. Whenever we have wanted to see deeper into the structure of matter, the path has been the same. Increase the energy, and the universe reveals a new layer. It's a simple rule, but it carries a quiet tension. If seeing smaller always demands more energy, you might wonder, why stop? In principle, you could imagine building bigger and bigger accelerators using higher and higher energies, peeling back level after level of structure, forever. No smallest distance, no ultimate layer, just a continuous zoom into an endlessly divisible world. But physics hints that this isn't how reality behaves. The more energy you concentrate into a tiny region, the less you can treat space as a passive background. At everyday scales, the stage on which particles move is flat and reliable. At higher energies, the stage itself begins to bend. Gravity, which is almost invisible in the world of atoms, slowly wakes up. And there's another complication. So far, we've mostly talked about using light as our way of seeing the universe. Light has been our main messenger, from simple lenses all the way to enormous telescopes in orbit. But when we push light to shorter and shorter wavelengths to see finer details, we also make it harsher and more violent. At some point, the very thing we're using to look starts to damage what we're trying to see. If light has been our guide to the universe for as long as we've been able to see, it's natural to assume it can show us everything. We build telescopes to read the glow of distant galaxies, cameras to capture faint stars, and microscopes to reveal the hidden world in a drop of water. Light feels like the perfect messenger. So, why does it fail us when we ask it to show us something as small as an atom? And why do humble electrons succeed where light falls short? The problem isn't that our lenses aren't good enough, or that our detectors aren't sensitive enough. The limit is built into the waves themselves. Any wave, whether it's ripples on a pond, sound in the air, or light in a vacuum, can only resolve details down to around its own wavelength. Try to use waves that are too long compared to the structure you care about, and the fine details simply vanish. Visible light, the soft glow our eyes evolved to see, has wavelengths of a few hundred nanometers. That's tiny compared to everyday objects, but an atom is only about 1/10 of a nanometer across. Asking visible light to outline an atom is like trying to trace the edge of a single grain of sand using a brush as thick as a rope. The wave wraps around it, smoothing out the sharp corners, and all you see is blur. You can imagine dropping a large stone into a lake and watching big, gentle waves roll across the surface. Those waves are wonderful for telling you that something disturbed the water, but they won't give you any clue about the fine texture of a pebble on the lake bed. To sense something that small, you'd want tiny, closely spaced ripples instead, shorter wavelengths. Physicists took that hint seriously. If the key to sharpening our vision is shorter wavelengths, then we need radiation with wavelengths much smaller than visible light. X-rays provide exactly that. Their wavelengths are comparable to the spacing between atoms in a crystal lattice, and that lets them probe structures on atomic scales. When a beam of X-rays passes through a crystal, it doesn't just cast a shadow, it creates a distinctive diffraction pattern, bright and dark spots spread across a detector. From that delicate pattern, scientists can reconstruct the positions of atoms, almost like reading a barcode written in light. This is the basis of X-ray crystallography, the technique that revealed the double helix shape of DNA and countless other molecular structures. But there's a price to pay. Shorter wavelength means higher energy, and higher energy photons are not gentle observers. They can knock electrons out of atoms, break chemical bonds, and rearrange the very structure they're supposed to be revealing. Use too intense a beam or stare at the same spot for too long, and the sample starts to change under the assault. At these scales, the act of looking becomes a kind of touch, one that can bruise. That's where electrons quietly step in. Quantum mechanics tells us that every particle has a wave-like side. The de Broglie relation connects a particle's momentum to an effective wavelength. For electrons, we can control that momentum by adjusting their energy in an electric field. Turn the knob, and their wavelength shrinks or grows, just like tuning an instrument. In the 1920s, the Davison-Germer experiment showed that electrons really do behave like waves. When fired at a crystal of nickel, the electrons produced a diffraction pattern, just as X-rays would. It was as if the crystal were a three-dimensional grating, and the electrons were ripples being scattered and recombined. The pattern on the detector wasn't random. It carried information about the spacing and arrangement of atoms inside the crystal. That realization unlocked a new kind of vision. By accelerating electrons to a few hundred or a few thousand electron volts, their wavelengths become much smaller than those of visible light and comfortably in the range needed to explore atoms and even finer details. Yet their energies can be kept low enough that they don't blast the sample apart with every pass. They interact strongly, so you don't need a vast number of them, and you can focus them into thin beams. Out of this, the electron microscope was born. Instead of glass lenses, these microscopes use magnetic fields to bend and focus beams of electrons, guiding them through vacuum chambers and onto thin samples. When the electrons pass through or bounce off the material, they carry with them subtle information about the internal structure. On a screen or detector, those tiny shifts in direction and intensity build up into images where individual columns of atoms can be picked out, like beads on a string. For many structures, electrons are the kinder way to look closely. To get a certain resolution, photons would have to be pushed to ferocious energies. Electrons can achieve similar resolving power with far less violence. They give us a way to map the atomic landscape without immediately tearing it apart. Still, the rule we met earlier hasn't gone away. Whether we use photons or electrons, the pattern is the same. To probe smaller distances, we must use higher energies. At modest energies, electrons gently sketch the outlines of atoms and lattice planes. Raise the energy further, and they become probes of the atomic nucleus itself, scattering off its inner contents and hinting at deeper layers, quarks and gluons hiding within. As our instruments evolved from tabletop microscopes to long linear accelerators, the electron beam turned into a kind of surgical spotlight aimed at matter's heart. By watching how those high-energy electrons are deflected, physicists learned that protons are not featureless spheres but complicated bound states, full of internal motion and structure. In that way, electrons have served a double role in our story. First, as delicate artists, drawing the architecture of atoms and molecules. Later, as projectiles and powerful machines, revealing that even the nucleus is not an indivisible dot, but a world with its own storms and patterns. And although gravity still feels distant from this discussion, the path we're on, using ever higher energies to reveal ever smaller distances, will eventually collide with it. For now, though, following the electrons a little farther will carry us from the calm outlines of atoms into the restless interior of the nucleus, where quarks, gluons, and a surprising amount of emptiness wait to be uncovered. When people first heard that an atom is mostly empty space, it sounded almost like a joke. You take something as solid as a piece of gold, and the physics story says that, on the inside, it's nearly all nothing. That strange idea came from a simple, almost old-fashioned experiment. Early in the 20th century, Ernest Rutherford and his colleagues took a very thin sheet of gold and fired tiny, positively charged particles at it. If atoms were something like a soft, uniform pudding of charge, those particles should have drifted through with only gentle nudges. Instead, a few of them bounced almost straight back. Rutherford famously said, "It was as surprising as firing a shell at a piece of tissue paper and having it come back and hit you. Most of the particles sailed through as if there was nothing there at all, but a small fraction hit something so concentrated, so dense, that they rebounded sharply." From that quiet little experiment, the picture of the atom changed. Now, instead of a solid ball, an atom looked more like a tiny solar system. Almost all of its mass lived in a nucleus thousands of times smaller than the atom itself, with a light, fuzzy cloud of electrons around it. If the atom were blown up to the size of a sports stadium, the nucleus would be something like a grain of sand at the center. Everything else would be empty seats and air. For a while, that was enough of a revelation. The atom was mostly nothing, and the nucleus was the hard, indivisible heart. But curiosity doesn't stop at good enough. Once you accept that ordinary matter is structured, it's hard not to ask the next question. If the atom is almost all empty space with a small, dense center, what about that center itself? Is the nucleus a solid, featureless lump? Or is it hiding more layers the way the atom once did? You can't answer that with a tabletop scattering experiment anymore. To probe something that small, you need electrons moving with energies far beyond what a simple lab setup can give. That's where large accelerators came in. On the hills above Stanford University in California, scientists built a machine called the Stanford Linear Accelerator, or SLAC. It was essentially a 2-kilometer-long electron gun, a straight line carved into the Earth, designed to launch electrons to enormous energies and smash them into protons and neutrons. Those experiments, called deep-inelastic scattering, were like Rutherford's gold foil test turned up to an almost unthinkable scale. The idea was the same: fire a beam of charged particles at a target and carefully measure how they bounce. But now, the bullets were so energetic, and their wavelengths so short, that they could resolve details deep inside the nucleus. If the proton were truly solid, the electrons should scatter as if they were hitting a tiny uniform ball of charge. Instead, the data told a different story. The pattern of angles and energies looked as though the electrons were ricocheting off several smaller, more concentrated regions inside each proton and neutron. It was as if Rutherford's cannon shell had not hit a single stone at the center of the stadium, but 3 smaller stones orbiting inside that central space. From this, physicists inferred that protons and neutrons are themselves composite. They're made of more fundamental entities, quarks, bound together by a very strong interaction mediated by particles called gluons. What had looked like a single hard particle turned out to be another level of structure. The theory that describes this, quantum chromodynamics, is both elegant and deeply counterintuitive. Quarks come in different colors, not literally in the way our eyes see, but as a kind of charge for the strong force. Gluons carry this color charge between quarks, stitching them together. And unlike the familiar electric force, which gets weaker as charges move apart, the strong force does something unusual: pull quarks away from each other, and the binding doesn't fade, it tightens. A common picture is that of a rubber band. At small separations, you hardly feel any tension. Stretch it out, and the resistance grows. Try to pull two quarks completely apart, and the energy you pour in doesn't give you a free quark. Instead, it becomes so large that it creates a new quark-antiquark pair, snapping the system into two bound states again. In nature, quarks never roam alone. They are permanently confined inside larger particles. Inside a proton, the situation is even more complex than three quarks simply sitting in place. Those three valence quarks are surrounded by a restless sea of gluons and short-lived quark-antiquark pairs that constantly wink into and out of existence. The strong force fields surge and fluctuate, creating a dynamic, churning environment. If you could somehow shrink yourself down and drift inside a proton, you wouldn't find a tiny marble with three dots embedded in it. You'd find something more like a constantly shifting storm of energy and fields, with quarks and gluons flashing in and out, interacting, merging, and separating. The solid particle is really a knot of activity. A pattern in a field is stable only when viewed from far away. That picture leads to a quiet but profound realization. The matter that feels so solid under your hand is mostly structure imposed on emptiness. At the scale of the atom, it's empty space with a nucleus in the middle. At the scale of the nucleus, it's fields and fluctuations, with most of the volume holding very little rest mass at all. What we call stuff is largely the organization of energy, not simple, crowded substance. To reveal this hidden interior, nature didn't give us a direct window. We had to build one out of metal, magnets, and vacuum. Machines like SLAC were not just big scientific toys. They were microscopes made of stone and steel, devices that turned energy into vision. By studying how electron beams scatter, by sifting through countless collisions, physicists reconstructed the inner life of the proton and found that emptiness and activity coexist at the core of matter. And even that was only the beginning. Once we learned that protons and neutrons are intricate bundles of quarks and gluons, a new question emerged. What else might be hiding, not inside particles, but in the fabric of the universe itself? By the time physicists had learned to read the storm inside the proton, they had also learned something else. The deeper you want to look, the more energy you have to spend. Those early scattering experiments, like the ones at SLAC, were already impressive feats of engineering, but they were still, in a sense, narrow flashlights shining into a very small corner of the quantum world. To push further, to probe smaller distances and stranger fields, you would need something on an entirely different scale. You would need a machine that doesn't just nudge matter, but briefly recreates the kinds of energies that existed in the first fractions of a second after the Big Bang. That is where the Large Hadron Collider comes into the story, not as a science fiction device, but as a very real ring of magnets buried beneath the countryside near Geneva. It's a circle about 17 miles or 27 kilometers around, tucked quietly under farmland and villages. Inside that loop, beams of protons are guided by powerful superconducting magnets, accelerated again and again until they are moving at just a hair less than the speed of light. Each proton in those beams carries an energy of about 7 trillion electron volts. When two beams collide head-on, the total energy available in that tiny point in space climbs to around 14 trillion electron volts. It can be helpful to think of the LHC as a kind of microscope, even if it looks nothing like glass and lenses. In an ordinary microscope, you change the wavelength of light to adjust what you can resolve. With the LHC, you change the energy of the particles you collide. The higher their energy, the shorter the effective wavelength, and the smaller the structures you can in principle explore. Instead of focusing light on a slide, you focus proton beams onto each other, turning kinetic energy into a brief, concentrated knot of fields and particles. For a moment, the densities can approach those that once filled the entire young universe. One of the major goals of this machine was to tap the Higgs field, the field that quietly fills all of space and gives mass to elementary particles. In the equations, that field is always there, but to see its presence directly, you have to hit it hard enough to make it ring. At the LHC, that ringing appears as a Higgs boson, a particle that exists only for a tiny fraction of a second before it decays into other particles. Detecting it is a little like spotting a single, faint ripple in a pond after throwing in an enormous stone, while thousands of other waves are crashing in at the same time. To catch such subtle signatures, the LHC uses enormous detectors with names like Atlas and CMS. These detectors are not small instruments you hold in your hand. They are multi-story structures, as tall as buildings, wrapped around the collision points like three-dimensional cameras. Layers of different materials track the paths of charged particles, measure their energies, and record how they interact. Whenever two proton beams cross and a collision happens, hundreds of sensors fire at once, and those signals are converted into digital patterns that tell scientists what emerged from that burst of energy. Most of the time, the collisions produce very familiar debris, showers of particles that follow well-understood rules. Only a tiny fraction are interesting in the sense that they might involve rare processes, like the creation of a Higgs boson or some other, more exotic particle. The challenge is that the LHC produces millions of collisions every second. It is as if you are trying to listen for a single whispered word in a crowded stadium full of people talking. To cope with this, the detectors use multiple layers of triggers, automatic decision systems that throw away the vast majority of events and keep only those that might hold something new. Even after that filtering, the amount of data is staggering. Petabytes of information flow out of the detectors and into computing centers around the world. No single lab can handle all of it, so the processing is distributed over a global grid of computers. Teams of physicists spend years refining their analyses, checking for tiny bumps in graphs, small deviations from what the known physics predicts. When the Higgs boson was finally announced, it wasn't because someone had seen it flash by on a screen. It was because, after careful counting and cross-checking, a small, persistent excess of events appeared exactly where theories said a Higgs-like particle should be. From the outside, the LHC can look like an aggressive machine. Protons slam together at incredible energies, magnets humming at cryogenic temperatures. But there is another way to see it. It is a remarkably calm, methodical eye on the quantum world. The collisions themselves are violent on a microscopic scale, but the overall operation is controlled, steady, almost gentle in its pacing. Night after night, while most of the world sleeps, beams circulate in the ring, collide at fixed points, and quietly reveal the inner rules of matter and energy. And yet, for all its power, the LHC is still not enough to reach the scales where gravity and quantum mechanics fully intertwine. The distances it can probe, on the order of 10-16 meters, are incredibly small, far below the size of a proton, but still unimaginably larger than the Planck length of about 1035 meters. The energies in each collision are enormous by human standards, but they are tiny compared to the Planck energy, the scale at which space-time itself is expected to become wildly quantum and unruly. It's like examining the grain of a piece of wood and wondering what happens if you keep zooming in until even the atoms stop making sense. If you keep following the logic that has guided physics so far, the path seems clear. Build larger machines, reach higher energies, and you should be able to resolve ever smaller details. However, there is a quiet warning built into the fabric of the universe. Energy is not just a way to sharpen your view. Energy also has weight, and weight curves space-time. When you concentrate enough energy into a small enough region, you do not simply turn up the contrast on your cosmic microscope. You begin to disturb the stage on which the experiment is being performed. The LHC does not yet reach the regime where this becomes an immediate problem, but the trend is there if you extrapolate. Push the idea far enough, and a strange possibility appears. By trying to look too closely, you might create a tiny black hole that hides the very region you want to examine. Instead of revealing finer structure, more energy could eventually make reality itself fade behind an event horizon. At that point, the straightforward rule, more energy, smaller scales, stops being a simple invitation and starts to sound like a bargain with a price. So, the Great Ring beneath Geneva serves two roles in our story. It is humanity's most powerful tool for peering into the quantum world, and a reminder that our usual intuition about seeing more by pushing harder may not hold forever. We can keep extending the reach of our machines for a while, but there comes a point where the universe itself begins to resist. That is where gravity steps in, not as a gentle background influence, but as an active participant, bending space-time in response to the energy we use, and hinting that the road to smaller distances might end in darkness rather than detail. For most of our journey so far, the rule has seemed simple. If you want to see smaller things, you pay with more energy. More powerful microscopes, higher energy beams, sharper and sharper focus. It feels like a bargain the universe is happy to honor, at least at first. But if you follow that rule far enough, something uneasy begins to appear at the edge of the story. Imagine you're trying to inspect a tiny speck of dust on a table. With a dim lamp, you only see the outline. Turn the lamp up, the details sharpen. Turn it up more, and more features come into view. Now, picture taking that idea to an extreme. You don't just brighten the lamp. You concentrate the light into a smaller and smaller spot, pouring more and more energy into that single, shrinking region. At some point, you're not just illuminating the speck anymore, you're scorching the table. In physics, we do something similar when we try to probe very small distances. To localize a particle more precisely, to say it's right here inside this incredibly tiny region, you have to use probes with very short wavelengths, which means very high energies. We've already seen that with electron microscopes, and then with gigantic colliders like the LHC. Each step up in energy lets us peel back another layer of structure. But there is a quiet complication that comes from Einstein. Energy and mass are two faces of the same thing. A packet of light with huge energy behaves gravitationally as if it has mass, and mass curves space-time. So, the more energy you cram into a tiny region to sharpen your view, the more you start bending the very fabric you're trying to examine. A helpful way to picture this is to think of a flexible rubber sheet. If you place a small marble on it, there's a slight dent. Put a bowling ball on it, and the sheet curves deeply around the ball. Gravity does something similar to space-time. A little mass makes a gentle dimple. A lot of mass, squeezed into a very small volume, can produce an extreme curvature, a deep well from which nothing can climb out. In the language of general relativity, every amount of mass energy has an associated gravitational radius, called the Schwarzschild radius. For something like the Earth, that radius is far smaller than the planet itself, buried deep inside. But if you took the Earth's mass and somehow compressed it down inside that radius, space-time would fold in on itself, and you would form a black hole. Light wouldn't escape, information wouldn't escape. The surface where escape becomes impossible is what we call the event horizon. Now bring that idea back to our quantum microscope. Each time we try to look at smaller distances, we pile more energy into a smaller region of space, hoping to tease out finer details. At moderate energies, space-time is basically unbothered. It behaves like a smooth, passive background. But if you keep pushing, raising the energy, shrinking the spot you're focusing on, you eventually reach a strange threshold. When the size of the region you're probing becomes comparable to the Schwarzschild radius of the energy you've put in, gravity wins. Instead of giving you a sharper picture, the experiment creates a tiny horizon, A miniature black hole forms, trapping whatever was inside behind an invisible boundary. The very act of trying to see more causes the object of your curiosity to disappear. You could try to push harder, add even more energy, squeeze the region even smaller, but that only makes the horizon grow. The black hole gets larger, not the details. From the outside, all you can observe is a dark patch, and, if Hawking's ideas are right, a faint whisper of radiation as the black hole slowly evaporates. The fine structure inside, the thing you were trying to resolve, never makes it back out in a readable way. This is what people sometimes call the black hole barrier. It's a limit that doesn't come from our engineering skills or the current size of our machines, but from the interplay of quantum mechanics and gravity. Below a certain scale, the usual strategy of more energy, finer resolution turns on itself. The microscope collapses into the thing it was meant to observe. The number that marks this boundary is built from the constants of nature, the speed of light, the strength of gravity, and Planck's constant, which measures the graininess of the quantum world. When you combine them in just the right way, you get a length of about 1.6 Acadie 1035 meters, the Planck length. At that scale, the Schwarzschild radius associated with a probe's energy and the quantum wavelength used to localize it become comparable. Push beyond that, and any attempt to confine energy more tightly just gives you a horizon instead of a clearer image. In other words, the black hole barrier seems to say, there is a shortest meaningful distance beyond which the concept of where stops working the way we expect. Not because we lack imagination, not because our instruments are clumsy, but because space-time itself refuses to cooperate. You can keep trading energy for resolution up to a point, and then the exchange rate suddenly collapses. The universe draws a curtain, and what lies behind that curtain is described not by familiar coordinates, but by something deeper and stranger. There's something quietly poetic about this limit. The same phenomenon that shapes galaxies and swallows stars, gravity collapsing matter into black holes, also appears as a guardrail on our efforts to probe the tiniest corners of reality. The physics of the very large and the very small meet at a single frontier, and on the other side, our usual picture of continuous space and time may not survive. For now, the black hole barrier is mostly a thought experiment, a way of combining what we know about quantum mechanics and general relativity and asking, what happens if we push both to their extremes? But that thought experiment carries a clear message. There is a scale where our ordinary tools, our familiar equations, and even our intuition about distance stop being trustworthy guides. To understand what truly lives near that frontier, physicists have turned to a different kind of construction project, not in the ground like the LHC, but in the space of ideas. Instead of building larger rings and stronger magnets, they have tried to build natural units of length, time, and energy directly from the constants of the universe itself. Those units, the Planck units, give that mysterious boundary a name and a scale, and they hint that the early universe, and perhaps the very fabric of space, might be woven from something more discrete and pixel-like than the smooth continuum we're used to. By this point in the journey, it feels as if the universe has done something a little mischievous. Every time we tried to see smaller, it let us trade energy for resolution, until gravity quietly stepped in and turned our microscope into a black hole. That barrier feels so abrupt that it raises a natural question. If there really is a hard edge to distance, can we give that edge an actual number? One way physicists try to answer that is by stepping back from any particular experiment and asking, what kind of measuring sticks would the universe build if it had to choose its own units? In our everyday lives, units are human inventions. A meter, a foot, a second. These were defined by the size of the planet, or the swing of a pendulum, or vibrations of atoms in a lab. They're convenient, but they're arbitrary. Nature doesn't know what a yardstick is. So instead of starting with things in our world, we can start with the deep constants that show up in our equations over and over again. There are 3 of them that are especially important for this story. The The first is the speed of light, c, which tells us how fast information can move and how space and time are woven together. The second is Newton's gravitational constant, g, which measures how strongly mass and energy curve space-time. And the third is Planck's constant, h, which sets the scale of quantum uncertainty and tells us how grainy the quantum world is. If you hand these three numbers to a good mathematician and ask, can you build a unit of length, a unit of time, and a unit of energy just out of these? The answer is yes, and those units are called the Planck length, the Planck time, and the Planck energy. You don't need the exact formulas to appreciate what they mean. What matters is that they're not based on any particular object, no metal bar in a vault, no atomic clock on a satellite. They're built purely from the way relativity, gravity, and quantum mechanics talk to each other. They are, in a sense, the most natural rulers and clocks the universe could choose. When you put the numbers in, the Planck length comes out to about 0. You're 16 meters. Or more simply, 10 to the minus 35 meters. If a proton were enlarged to the size of the observable universe, the Planck length would still be a tiny dot inside it. It's so far beyond our direct reach that it almost feels like fiction. And yet, this is the scale where the quantum jitter of fields and the curvature of space-time become equally strong. Below this length, our current theories simply don't know how to behave. The Planck time is just as extreme. It's around 10 to the minus 44 seconds. That's the time it would take light, racing at its maximum speed, to cross one Planck length. Below that time scale, the distinction between before and after becomes blurry. Our concept of a continuous timeline starts to lose its grip. If you wind the universe back in time toward the Big Bang, you eventually hit this boundary. There is a period known as the Planck era, those first unimaginably small fractions of a second up to about 1 Planck time after the beginning. In that era, densities and temperatures were so high that our usual separation between forces and fields breaks down. Gravity was not a gentle background curve. It was as wild and quantum as everything else. The trouble is, we cannot see that era directly. When we look into the night sky with telescopes, even with our most sensitive instruments, the farthest back in time we can actually image is not the Big Bang itself, but a kind of baby picture taken when the universe was about 300,000 to 400,000 years old. That's the cosmic microwave background, fossil light released when the universe cooled enough for atoms to form and the fog of free electrons cleared. Before that, the universe was opaque to light. Photons bounced around like beams in a dense fog, unable to travel freely. So, there is a wall made of light itself that hides everything earlier than that age from direct view. The Planck era sits far beyond that wall, deeper in the past by an almost unimaginable factor. And yet, gravity gives us a way to at least infer that something strange happens there. When you study black holes, you find a surprising pattern. A black hole has entropy, a measure of how many internal states it could have, and therefore a measure of how much information it can contain. Jacob Bekenstein and Stephen Hawking showed that this entropy is not proportional to the volume inside the horizon, but to the area of the horizon itself. And that area is naturally measured in squares of the Planck length. In other words, if you covered the surface of a black hole's event horizon with tiny squares, each one a Planck length by a Planck length, the number of such squares is directly related to the maximum information content of the black hole. It's as if nature is quietly telling us, this surface is made of Planck-sized pixels of information. That idea is what led to what we now call the holographic principle. In a familiar hologram, a two-dimensional plate encodes a three-dimensional image. In gravity, something similar seems to happen. The information about everything that falls into a region may be stored not in the bulk volume, but on the boundary surface, in these tiny Planck-scale bits. It's a radical shift in perspective. We like to think of reality as three-dimensional space filled with particles and fields, and time flowing steadily along. But at the edge of our best theories, a different picture begins to appear. One in which the fundamental description looks more like a pattern of information living on a surface or on a network, and space and time are emergent summaries of that deeper pattern. If that's true, then the Planck length is not just a mathematical curiosity. It's the size of the smallest meaningful chunk of area in the theory, the smallest pixel into which space-time can be divided while still making sense. Below that scale, asking for a sharper division of space may simply be asking the wrong kind of question. Once you start thinking this way, our old notions of measurement begin to feel incomplete. Quantum mechanics already told us we cannot know position and momentum with arbitrary precision. Now, gravity and holography are hinting that there may be a built-in minimum fuzziness to space itself, enforced at the Planck scale. There might be a shortest distance, a smallest area, a briefest moment, beyond which the language of coordinates and rulers simply doesn't apply. And if there really is a fundamental grain to space-time, measured in Planck units and encoded in these holographic pixels of information, then even the uncertainty principle has to be revisited. Because every time we try to pin something down more tightly, every time we reach for a finer resolution, we're not just fighting quantum jitter anymore. We're also tugging on gravity and bending the very grid we're trying to draw. So, the next step in our journey is to see what happens when those two ideas collide. The familiar quantum uncertainty you may have heard about, and this new gravitational limit tied to black holes and Planck scale pixels. When they meet, they merge into a generalized rule, one that suggests there really is a smallest blur, a minimum distance that no clever experiment can beat. To see what happens when uncertainty and gravity meet, it's helpful to return, just for a moment, to the original rule that started all of this. In the quantum world, you never get to pin everything down at once. In the early days of quantum mechanics, Werner Heisenberg realized that if you try to measure a particle's position more and more precisely, you inevitably lose track of its momentum, and vice versa. This isn't about clumsy instruments or human error. It's built into the mathematics of the theory itself. The sharper you make one number, the more the other one must blur. You can picture it like trying to photograph a hummingbird in a dark garden. If you keep the shutter open for a long time, you see the path of its motion, but its location becomes a streak. If you shorten the exposure to freeze a single moment, you get a crisp position, but the path disappears. In quantum mechanics, something like this trade-off is not just a limitation of cameras, it's the way reality is encoded. Mathematically, the rule says that the uncertainty in position and the uncertainty in momentum multiply to something at least as large as Planck's constant. There is always a minimum area of fuzziness in this little phase space of possibilities. We can shrink that area, shape it, trade position against momentum, but we can never compress it down to a single sharp point. Now, imagine you want to localize a particle more tightly. Operationally, that means you shine light on it with shorter and shorter wavelengths, because shorter wavelengths can resolve smaller details. High-frequency photons carry more energy. So, as you demand a more precise position, the photons you use must be more energetic. That's quantum field theory's way of enforcing the uncertainty principle in the lab. For a while, this works exactly the way textbooks say it should. You use brighter, higher energy light to probe smaller and smaller regions, and the uncertainty in position shrinks. The momentum gets fuzzier, but your where becomes crisper. In a world with no gravity, you can, at least in principle, keep dialing this up as far as you like. But we do not live in a world without gravity. Once the energy of your probing photon becomes extremely high, general relativity quietly walks onto the stage. Energy and mass are interchangeable, and mass and energy both curve space-time. So, when you concentrate an enormous amount of energy into a tiny region to see an object more clearly, you are also strengthening gravity in that region. At first, that gravitational effect is negligible, but as you push to absurdly high energies, something dramatic happens. The energy packed into that small volume curves space-time so strongly that a little event horizon can form. Instead of revealing more detail, your experiment creates a microscopic black hole. The very act of trying to look more closely causes the region you're looking at to slip behind a curtain from which no light can escape. In that regime, adding more energy doesn't sharpen your picture. It enlarges the horizon. The object you were trying to measure is now hidden. And the more fiercely you try, the worse it gets. The strategy that works so well in ordinary quantum mechanics has completely backfired. Physicists have tried to fold this gravitational back reaction into the uncertainty principle itself. The result is what's called the Generalized Uncertainty Principle. Instead of uncertainty in position shrinking smoothly toward zero as you increase momentum uncertainty, there's an extra term, a gravitational correction. At low energies, you recover Heisenberg's familiar rule. But as momentum grows huge, the new term dominates, and the uncertainty in position starts to grow again. If you draw this relationship on a simple sketch, it no longer looks like a simple hyperbola sliding gently toward the axis. It looks like a curve that dips down, reaches a minimum, and then swings back up. There's a sweet spot, a smallest possible fuzziness in position. No matter how clever the experiment, no matter what probe you use, you cannot beat that minimum. Try harder, and gravity blurs the picture for you. That minimum distance is naturally of the order of the Planck length. In this view, the Planck scale is not just a convenient combination of constants. It is the scale at which our attempts to define here run into a brick wall made of black holes and quantum jitter. Lengths smaller than this don't just fail to show up on our instruments. The very notion of length stops behaving the way we expect. This dovetails beautifully with the hints from holography. If a finite patch of space can only contain a finite amount of information, and that information grows with the boundary area measured in Planck units, then there is a maximum number of distinguishable cells you can fit into that region. The Generalized Uncertainty Principle is one way of saying you can't mark those cells more finely than the universe allows. There is a limit to how many separate places can be meaningfully defined. Another way to say it is that space-time refuses to be perfectly sharp at arbitrarily small scales. Heisenberg already told us that particles could not be perfect points in phase space. Now gravity adds that space-time itself cannot be a perfectly smooth, infinitely divisible sheet. There is a built-in grain, a deep blur, that protects the theory from collapse. All of this is still an active area of research. The precise form of the Generalized Uncertainty Principle depends on the model, and we don't yet have direct experimental access to Planck-scale physics. But taken together, with black hole thermodynamics, with holographic entropy, with the strange behavior of information at horizons, a picture begins to emerge. The universe seems to be whispering that there is a fundamental limit to how fine-grained where can be. Once you accept that, a natural curiosity follows. If there really is a minimum length, perhaps the objects we call particles are not truly featureless points at all. Maybe the ingredients of matter themselves are extended in just the right way so that when you try to cram more and more energy into them, they do not focus that energy into a singular point, but spread it out over a tiny but finite size. That line of thought leads directly into some of the boldest ideas in modern theoretical physics, frameworks in which the smallest building blocks are not dots but tiny vibrating strands, and where the existence of a minimum length is woven into the structure of matter from the very beginning. By the time physicists had followed the trail of higher and higher energies, an uncomfortable pattern kept appearing in the equations. Treat particles as perfect mathematical points, and at extreme energies the calculations often blow up into infinities. Forces become infinitely strong at a single location. Curvature of space-time diverges, and the neat fabric of the theory tears. It's as if nature is telling us, very quietly, that it doesn't like having everything squeezed into a mathematical dot. That raised a simple but radical question. What if particles weren't points at all? Imagine replacing each point-like particle with a tiny loop or segment of string, so small that under ordinary conditions it looks like a dot. Instead of being structureless, this string can vibrate in different ways. One pattern of vibration looks from far away like an electron. Another pattern looks like a quark. Another carries the properties of a photon. And one very special mode carries exactly the quantum numbers you would expect from a graviton, the hypothetical quantum of gravity. Suddenly, the infinities begin to soften. When two strings collide at enormous energy, the energy doesn't concentrate in a single mathematical point. It's smeared out along the length of the string. The interactions become more like two rubber bands slapping and tangling than two hard bullets smashing together. The dreaded singular spikes in the equations are replaced by gentler, more manageable behavior. You can picture this with a simple analogy. If you poke a soap bubble with the tip of a needle, you get a clean puncture and the surface tears. If you press against it with a finger, the force spreads out and the bubble can flex. String theory replaces needles with fingers. At the Planck scale, the sharpness of interactions is limited by the fact that everything has a little bit of length built in. In this framework, there is a characteristic size to the fundamental string, typically taken to be very close to the Planck length. Below that scale, the notion of probing smaller distances starts to lose meaning. When you increase the energy in a collision, you don't make your probe sharper and sharper. Instead, you excite the string into higher vibrational states. It can stretch, oscillate, and wrap, but it doesn't allow you to focus the interaction into something smaller than the string itself. That behavior gives a new way to think about the minimum length we met earlier. The Generalized Uncertainty Principle suggested that no measurement could resolve distances smaller than a certain limit, because gravity would intervene and form tiny horizons. String theory builds something similar directly into the ingredients of matter. The constituents themselves simply don't have features on scales shorter than their own length. The theory comes with a built-in blur, a natural cutoff that keeps the mathematics from collapsing. To make all of this work, however, the theory asks for more room than our everyday three spatial dimensions. When you write down consistent string equations, they typically want 9 or 10 spatial dimensions, plus time. The extra directions aren't visible to us at human scales. They're thought to be curled up, compactified into shapes so small that even our most powerful experiments can't resolve them. Those hidden shapes aren't arbitrary decorations. The way they curl into intricate surfaces with folds and holes known as Calabi-Yau manifolds helps determine the vibrational patterns allowed for the strings. Different internal geometries can lead to different particle spectra, different forces, different apparent laws of physics in the larger three-dimensional world. In that sense, the tiny hidden structure of space can tune what kind of universe emerges at large scales. This has led to the idea of a vast landscape of possible stringy universes. In principle, there might be an enormous number of self-consistent ways to curl those extra dimensions, each giving rise to a slightly different set of particles and interactions. Our own observable cosmos would be just one small valley in that landscape, one particular arrangement where the strings hum in a way that permits galaxies, stars, chemistry, and eventually sleepy humans wondering about the Planck length. For our purposes tonight, though, the important message is simpler and more soothing. In the string picture, the universe refuses to let distances shrink beyond a certain point, because its basic ingredients are never truly point-like. At the tiniest scales, reality is more like a collection of ultra-fine threads, all vibrating and weaving together, than a grid of sharp mathematical dots. The apparent smoothness of spacetime is like a fabric viewed from far away. Look too closely, and instead of a sharp edge, you find strands. This is one possible way to save spacetime from the destructive tendencies we saw when gravity and quantum mechanics pull in opposite directions. Rather than letting energy concentrate into a singular point that tears the equations apart, strings spread that energy over a small but finite length. They soften high-energy collisions and naturally hint at a minimal, meaningful distance. Of course, not everyone is satisfied with starting from strings. Some physicists have taken a different route. Instead of giving particles a new internal structure, they ask whether the geometry of space and time itself could be quantized, broken into fundamental chunks. If space-time has its own underlying atoms, perhaps you don't need strings at all. You can start with the fabric instead of the threads, and see what kind of universe emerges when geometry comes in discrete pieces. After spending so much time treating space-time as a smooth, continuous fabric, some physicists began to wonder if that smoothness might be an illusion of distance. From far away, a sheet of paper looks perfectly flat. Under a microscope, it breaks into fibers. A coastline appears as a clean curve on a globe. When you stand on the beach, it's just grains of sand and broken shells. Maybe Einstein's graceful geometry works the same way. Maybe, deep down, space itself is made from tiny, indivisible pieces. This is the starting point for an idea called loop quantum gravity. Instead of adding new kinds of particles or stretching them into tiny strings, it asks a simpler but more radical question. What if we quantize geometry itself? In this view, space is not a blank container that things sit inside. It is a web of tiny relationships. The math describes a network, nodes connected by links, called a spin network. Each link carries a little quantum of area. Each node carries a little quantum of volume. You don't have a smooth continuum underneath everything. You have a graph-like structure where geometry comes in discrete units. From a distance, that network blurs together and behaves like the smooth space-time we're used to. Just as a woven fabric looks continuous until you get close enough to see the individual threads, the spin network only reveals itself at unimaginably small scales, around the Planck length. Below that, there is no smaller distance to talk about, because there are no smaller chunks of area or volume in the theory. This has a quiet but powerful consequence. There is no room for true singularities. In classical general relativity, if you compress enough mass into a small enough region, curvature can become infinite and the equations break. At the center of a black hole, or at the very beginning of the Big Bang, the math seems to point to a place where the theory simply stops making sense. In loop quantum gravity, you can never compress volume to literally zero. The spin network refuses to give you anything smaller than its own elementary building blocks. As you push matter and energy into a region, you hit a point where the geometry cannot shrink further in the way the classical equations demand. Instead of a singular point, you get a smallest possible volume with extremely high but finite energy density. Applied to the early universe, this opens the door to a different story about the beginning of time. Rather than a universe emerging from an infinitely dense dot, some models suggest a bounce. A previous contracting phase pushes energy into the smallest possible chunks of space. Quantum geometry resists further compression and effectively rebounds. In that picture, our Big Bang is not the absolute beginning of everything, but a transition, a turning point in the history of a much larger cosmic story. The same quantized geometry can be used to think about black holes. Instead of a region where curvature becomes infinite, a black hole interior becomes a place where the spin network is pushed into its most compressed configuration. The horizon area, in this language, is not a smooth surface but a large collection of tiny quantum patches, each carrying a small, fixed amount of area. Counting those patches in the right way hints at an explanation for why black holes have entropy at all, and why that entropy seems to scale with surface area rather than volume. If space-time really is granular at the Planck scale, it raises a natural question. Could we ever see traces of that graininess in the sky? One idea looks to very distant, very energetic events, gamma-ray bursts and flares from active galaxies. If the underlying geometry is slightly rough, then extremely high-energy photons might interact with that roughness just a little differently than low-energy photons. Over billions of light years, even a tiny difference could accumulate into a measurable delay. Two photons that left a distant explosion at the same moment might arrive at our telescopes, separated by a fraction of a second, with the higher energy one lagging behind or running slightly ahead. Space-based observatories have searched for exactly this kind of effect. So far, within the precision of our instruments, light of different energies seems to arrive in lockstep. If there is a granular structure, it must be extremely subtle, or hidden in ways we don't yet know how to tease out. Still, the search continues in the data, quietly in the background, waiting to catch even the smallest hint that space-time is not perfectly smooth. Another place to hunt is in the oldest light we can see, the cosmic microwave background. Tiny deviations in its pattern already tell us a rich story about the early universe. Some versions of loop-inspired cosmology predict delicate signatures in those fluctuations, little echoes of a bounce or of quantum geometry at very early times. So far, nothing has stood out as a clear fingerprint, but the door is not closed. Even without definitive experimental confirmation, the picture that emerges from this line of thinking is strangely calming. At the smallest scales, space is not a featureless void. It is a softly buzzing network of relationships, constantly being updated as matter and energy move and interact. The distances and volumes we talk about in everyday life are like average values, smoothed over a vast number of these microscopic building blocks. And there is a deeper hint tucked inside all of this. If geometry can be described as a network, then maybe geometry is not the most fundamental ingredient after all. Perhaps it is something that arises from even more basic data, patterns of connection, correlations, or quantum entanglement between underlying degrees of freedom. In that case, the fabric of space-time would not be primary. It would be a large-scale description of something more abstract. That idea brings us back to the Planck scale in a new way. We started by asking what happens when we push our notion of distance down to its limits, and we found both gravity and quantum mechanics protesting. Now, in both strings and loops, we see hints that distance itself might be a kind of approximation, useful and accurate at human scales, but not the deepest language the universe uses. From here, it's a short step to an even more unsettling thought. If space and time can emerge from patterns of information and entanglement, then the very act of measuring how far and how long may be more about relationships than about any underlying grid. And once you follow that thread, the question of what distance really means begins to soften into something more subtle and strangely peaceful. By now, we've followed two very different roads down into the small. One built from gravity, one built from quantum uncertainty. On one road, we kept pouring more and more energy into smaller and smaller regions, until gravity finally pushed back and wrapped those regions in tiny horizons. Look too closely, and what you're trying to see disappears behind a black hole boundary. On the other road, we sharpened our measurements until the uncertainty itself rebelled. Add gravity to Heisenberg's rule, and there comes a point where trying to pin position down any further only makes the blur worse. Both journeys stop at almost the same place, a length where our familiar ideas of distance and time simply refuse to cooperate. We call it the Planck scale, but that's really just our label for the point where general relativity and quantum mechanics both say very gently, my description doesn't work here anymore. Instead of taking that as a dead end, many physicists have started to treat it as a clue. If pushing our existing concepts harder only breaks them, maybe those concepts themselves are not fundamental. Maybe space and time are not the bedrock of reality, but the large-scale behavior of something more abstract, patterns of information, correlations, and entanglement. In holographic models, for example, the amount of information inside a region seems to scale with the area of its boundary, not with its volume. In some versions of quantum gravity, the closeness between 2 points in space can be rephrased as how strongly the underlying degrees of freedom are entangled. If you change the pattern of entanglement, you change the geometry. In that language, distance is not a fixed backdrop. It's a measure of relationship. From far away, this all smooths out into the calm space-time of Einstein, continuous, gently curving, good enough for planets and orbits and the everyday flow of time. But deep underneath, at the scales we've been drifting toward tonight, the picture may be less like a fabric and more like an invisible network. Nodes and links, bits and qubits, all quietly encoding where and when things can be. So, when we ask what happens at the Planck length, the most honest answer might be, the question itself starts to dissolve. The closer we try to inspect the smallest distance, the more nature hints that distance is a story we tell about something else. The universe doesn't become smaller or larger there. It simply stops speaking to us in the language of rulers and clocks, and starts speaking in the language of information and connections. If you've stayed with me all the way to this edge of understanding, thank you. If this slow walk through the deep smallness of reality brought you even a little calm, a gentle tap on, like, or subscribe is a tiny signal, but it helps this quiet corner of the internet keep glowing. I'd love to know where you're listening from, your city, your state, your country, and what time of night it is for you right now. For the rest of tonight, let yourself drift. Let the details fade, and keep only the feeling that you are part of a vast connected web of relationships the universe has been weaving for billions of years. Sleep well, and may your thoughts wander softly through the spaces between the stars.